Our next speaker is Ajay Brahmakshatriya, who's at MIT with his co-authors, and he's going to be talking to us about staging layouts for high-performance custom host network stacks. And Ajay is will soon be on the market, so if you're looking around, please make sure you come up to Ajay and have a chat with him later.
All right. Thanks for the introduction, Steve. Hi, everyone. My name is Ajay. I'll be presenting NetBlocks, which is I'll be showing you how to stage layouts to create this high-performance network stack. This is joint work with my collaborators, Rinard, Professor Manya, Ghobadi, and my advisor, Professor Saman, Amarasinghe. OK, so the motivation for this problem was very simple. A year ago, we were working on some high-performance network applications for data center settings, and we realized that there's a problem. When you start to write your applications, you basically have a choice of two protocols. There's UDP on one side, which is simple and fast, stateless, and has minimum overheads and works great. And on the other hand, you have TCP, which has in-order delivery, reliable delivery, maintains congestion control, does a lot of handshakes and stuff, but obviously comes with a lot of overhead. And if you happen to need something in the middle, where you say you need in-order delivery but not necessarily congestion control or something like that, you basically have to write things by your own. Like you have to spin up your own protocol from scratch. Why would you want something like this? The answer is also very simple. It's because of performance. Here I've shown a round-trip latency CDF for 10,000 requests for a echo application, basically. And these are the two extreme plots for UDP and TCP. As you can see, TCP is more expensive than UDP. But if you start adding other sort of protocols in the middle which implement individual sort of features like in-order delivery only, or checksumming only, or just some variations of the similar protocols, you can see that the performance is actually somewhere in the middle. But most importantly, it's actually quite far away from TCP. So if you start from UDP, but you only want in-order delivery, the only option you have is to go all the way to TCP, whereas you could be paying less based on what you're using. And this is what we essentially want to support. We want to carefully select features and pay only for what you're using. OK, simple problem. The simple solution is you wanted to build this sort of a modular stack called NetBlocks Core, or Network Stack Core, where you can essentially plug these features that you want, not just which features, but also what versions of them. Like you can implement reliability in different ways, or congestion control in different ways, and create your own stack. But not only that, we wanted to take this opportunity to also create a stack that's extensible, which means that the network engineers can also essentially implement their own small features that they can add onto the stack level itself to get more features than what is currently available. So in example, encryption. You could do encryption at the stack level so your application doesn't have to worry about it. And this happens all the time, by the way. Quick protocol, which is implemented by Google, does have some sort of encryption support at the stack level. OK, we started implementing this and quickly ran into a problem that many of you might have run into before, which is that writing high-performance code is really hard. When we start to write something like a modular stack like this, there's basically three approaches. The first is you write very hand-optimized implementations. We see this all the time. Like Quick is an example of something that is handwritten to be optimized. This implementation is obviously high performance. It's meant to be high performance. It is relatively easy to implement. Not for me, I'm not a network engineer, but for someone who has been writing network code for ages, they can write a good protocol in a few months, maybe. Yeah. But the problem with it is it's not general. Like you wrote an implementation, and that's what it does. You can't change it. If you change it, it's going to break, or it's going to not work as fast, or whatever. The other option is you make a network library where you can sort of like chain together stacks, and you can like layers can be attached together through some queues, and you can make your own custom protocols. This thing is obviously general because you're choosing what you want at the network or the library level. It is also easy to implement, maybe easier than the hand-optimized implementation. However, unfortunately, you pay the price through performance. You have this cost of abstraction that comes from the modularity that slows your whole process down. And since we are compiler engineers, our favorite option is to write a DSL compiler, or a compiler that can generate the stack for you. This has the added advantage of being high performance because you're generating specialized code for your specific implementation. It is also pretty general. You can generate a lot of protocols from a single compiler. However, it's not easy to implement. And what I mean by easy to implement here is if a network engineer comes around and wants to implement new features, they now have to learn how to write compilers, which we all know is pretty hard. At least I like to believe so. OK, so what we want is something in the middle, which is easy to implement, high performance, and general. By the way, this research is not sponsored by Google Chrome. This is just a coincidence. OK, so we set out to write this stack, and we tapped into our previous knowledge, which says that multi-stage programming or metaprogramming is a good solution for performant and general solutions. In this talk, I'll extend this to say that multi-stage programming is also easy to implement as long as it is done right. And the right way to do this, in my opinion, is to use our previous work, which is BuildIt. BuildIt is a type-based multi-stage programming framework embedded in C++. Before I go into how we're going to use this, I'm going to quickly explain what this means. So first, let's explain what multi-stage programming means in this context. A typical single-stage compilation workflow works like this. You write some source code, you compile it with your favorite compiler like GCC or Clang. You get an executable, you feed your input, and you get your output. That's single-stage compilation and execution. BuildIt generalizes this to multiple stages, where you have some source code, you compile it with your regular compiler like GCC or Clang, get an executable, feed in partial inputs. You provide parts of the inputs, and then you get as output more source code, which is specialized for those inputs. Compile it again with the compiler, get the executable, feed in rest of the inputs, and then get the final output. Again, this can be generalized to multiple layers, but multiple levels, but we'll be doing two-stage in this particular example. The thing I want to point out about this is BuildIt is purely a library approach, so all these compilers and toolchains that we are using along the way are standard compilers. There's no compiler sort of magic here, so it's very lightweight in that sense. And the second point I want to highlight is this is a very explicit form of multi-stage programming, which means that the output code that's specialized is produced as C code instead of some intermediate inside the compiler when you're using, like, say, C++ templates or something. OK, so with that in mind, let's just quickly go ahead and see how BuildIt works. BuildIt essentially introduces two new type templates, dynamic of var and static of var. Everything you write with dynamic of var is produced as it is. And everything you write with static of var is completely validated in the first stage. So here's an example. I have the power function, which has two inputs, base and exponent. I've marked the base to be dynamic of integer and exponent is static of integer. And since exponent is static, all the control flow, all the conditions based on that is completely evaluated to give us an unrolled code. And if I make a small change, if I make the base static and I make the exponent dynamic, you get something like that, where the control flow and the expressions based on the exponent are retained, whereas the base just becomes a constant in that code. OK, very simple programming model, two new type templates, wrap them around whatever you want, and you can get partial evaluation. So the way BuildIt internally works is it's a lot of magic in the sense like there's a lot of operator overloading that essentially extracts all the expressions that you write with dynamic variables. And for statements and control flow, we have this system where we repeatedly execute your code to explore all the branches and then combine those branches to give you basically a single code. There's a lot more details about this work in our previous paper, so feel free to look at it or come talk to me afterwards. But OK, that is a primitive that we have now to start building a network DSL. Let's get back to NetBlocks. What are the main challenges when you're writing a network sort of stack like this? The first problem is that these features that we're implementing change behavior globally. What I mean by that is, say I decide to enable a feature like reliability. And once I enable that, and the logic that sends the packet now needs to start attaching sequence numbers to it. The logic that receives the packet needs to checking if those acknowledgements have been received or send acknowledgements and so on. If there's a timeout happening somewhere, then you need to retransmit, duplicate acts and so on. You need to do handshakes and goodbyes and stuff like that. So which means a single feature can change a code in a lot of places. It's not like localized in one place. And the other big problem is that features affect state and structures globally. What this means is, again, in the case of reliability, once I enable it, I need to start putting sequence numbers into the packets. I need to keep a redelivery buffer for each connection that I have open. And I also need to change some global state to have like timers and stuff around. So a small feature can change the whole picture globally. So what we want is modularity, but that modularity obviously comes at the cost of performance or features. This is a problem. So what we noticed, however, in this case is that this modularity and all this configuration happens at the time of choosing the features. There is no runtime modularity. Like once you have decided your features and once you have decided the flavors of your features, everything is fixed. So in the staging system, if we can do all this modularity in the first stage and generate specialized code for your stack, some of these overheads can be eliminated. That's basically what we did. We implemented a high-performance aspect-oriented programming system. Aspect-oriented programming system, if you know. Yeah. So what we have essentially here is a NetBlocks framework. At the top is the application. At the bottom is the physical layer, which is basically handling all the physical communication between the nodes. And in between, we have the framework. The framework has in between these so-called paths, like the send path, the established path, ingress path, and so on, which correspond to roughly to the control paths that can be taken in the stack at runtime. And on the left, we have these modules, which implement these individual features. Now, what these modules can do is they can insert hooks into these paths to sort of change the behavior of that path. They can insert logic in any of these paths in a very modular, dynamic way. But we want to get rid of the overhead for that. So let's start with a simple implementation of aspect-oriented programming system. At the top, I have defined the module class, which is a generic sort of interface for all modules, and it has the virtual functions for all the hooks. Now, a module like reliability can sort of inherit from that and add hooks to, sorry, there should be an inheritance there, which I missed, apologies, which inherits from the module class and then implements those hooks as functions, which finally, there's a code that iterates through all the registered modules and invokes their hooks one by one and dispatches the calls. Now, what we do is, with a very small change, we basically first make all the parameters like the packets and the connection data structures as dynamic, so they will be generated. However, the module itself, like the modules here, themselves are static, which means that the registration of the modules, the configuration of the modules, the iterations of the modules, the virtual dispatches all happens in the first stage to give you very clean, inlined, optimized pack code that has the logic specifically for your feature. Not just choosing of modules. Now, within your modules, you can have if conditions based on like configuration parameters, which will generate different logic based on what features and what flavors are enabled. So that solves somewhat of a problem of sort of specializing for features. And with that, we implemented these 8 modules, which implement different features and their versions. On the right-hand side, I just don't need to get into all of this, but on the right-hand side, I just have like different options you have for these modules. And at the bottom, you can see that we can generate up to 864 different combinations from the same stack by just choosing different versions of the module. And this is even without specializing the stack for more optimizations like, which I'll talk about later about like data layout optimizations. So just by choosing features, we get these many flavors. Okay, so let's go to the next problem, which is about data layout changes because of features. So there are 2 types of sort of changes that can happen, or 2 types of events that can change the packet layout. The first is based on features. Like if you choose a particular feature, it might want to add headers or fields to your packets. Like if you enable congestion control, you need some congestion headers in your packet. And the second is based on deployment. What I mean by deployment here is the same protocol deployed in different scenarios might have different packet layouts. For example, one of the common fields that's there in all network protocols is the IP header. If we all have heard about this before, it's a 32-bit header which identifies where the packet is going, a host for the packet. But suppose you're deploying it in a scenario where you only have 16 nodes. Why do you want to play 32 bits for it? You can pack that whole thing into 4 bits and generate a very packed protocol. But at the same time, if you move to a different scenario, you need to recompile and generate a new protocol. What I'm saying is, as the deployment changes, the packet layout changes. We want a way to somehow programmatically change these layouts so that we don't have to manually go and change structures every time we are changing the protocol. We want somewhat like a staging of layouts, basically, like staging of code. So before I talk about my solution, let's just look at how it's currently implemented. Currently, if you look up at any network stack implementation, a library, or handwritten implementation, that's typically struct like these, which are packed struct, so they are all the fields are all next to each other, which sort of implement the layer. And then you take the pointer to the packet, cast it to one of these structs pointer, and then manipulate the fields. You can read or write them. That's the typical way of doing this. Obviously, this is not programmable. You cannot like remove fields at first stage. But one thing we noticed while looking at these implementations is that structs by themselves are not objects. They're not data. They are just a way of describing to the compiler how to access those particular fields. So we can make that explicit. We can convert this process of describing to the compiler how to access those fields as code, and then we already know how to stage code. So then we can stage those layouts. That's the simple idea that we came up with. So how it works is we require the user to describe each packet sort of header to us in this simple sort of structure where they have to give us 2 pieces of information. One is the size of a particular field, and the second is the alignment requirement of that field. With those 2 pieces of information, then we can compute the offset for each field by first taking recursively the offset of the previous field, then adding the size of the previous field and aligning it to the alignment requirement of this field, which is done here. And once we have the size and offset of each field, we can basically implement functions like getInteger or setInteger, which will compute the address of the field in the packet and then dereference it to give you the value. Obviously, all the computation of the address and stuff, this stuff happens in the first stage. So what you essentially get is a very tight code that just has the exact code to access those fields. And the way you use it is you create a packet structure, you add your fields to it, and then you can directly access your fields by calling them by name and setting those values. And that generates basically code on the right. This is great. We have sort of like described the problem as code, staged it, and we got some modularity out of it. But now what we can start doing is we can also further optimize it. We can say, OK, I know this field is going to have a specific range. So take this range as a value, and then compute the number of bits required for it. And in the getInteger implementation, now we can basically generate precise masking logic to get and set those fields. The good thing about this is the way you use these fields will exactly be the same. Nothing will change in the module implementation. The only thing that will change is how the fields are defined. And then the generated code will automatically have masks and shifts generated to do the actual bit manipulation. So this is great. We can now generate very precise layouts for our packets. One thing that NetBlocks automatically does for you is also, if you choose, it can rearrange the packets in such a way that the alignment requirements are satisfied while minimizing the number of bits required to have the whole packet implemented. So with this, what we have done is, here's a sort of a layout for a typical Ethernet, IP, UDP, and payload stack. We first identified some fields that are redundant, so things like length, which are implemented as part of IP and UDP both, or things like checksumming, which are again redundant, or things like in red, which are basically not useful in many scenarios, so we just drop them. And by removing all those, we get a packed layout like that. Furthermore, we did like the deployment optimizations where we said, OK, I know my hosts are only going to be 16 or in 4 bits range, so can you shrink them down and so on? And we get this very shrunk protocol that does almost UDP-like things for just a 2-byte headers, which is great for a scenario where you are throughput bound in ways. So one side benefit of this is because the compiler has all the information about your packet layout, it can just automatically generate packet inspectors for you that you can insert in Wireshark and just debug your custom ad hoc protocols that you're creating. So with this, comes the third part, which is about extending, which I promised would be very easy. And I don't have any slides for it. The easiest way I'm going to demonstrate that is by just implementing a new module right in front of you. So I have, So I have here the NetBlocks implementation that I have created. I'm going to quickly implement an encryption module, a dummy encryption module, and let's see how much effort it takes. So the first thing I would do is to implement a module header for a module class for it. So I've already implemented an encryption module here. All it has that's special is these 2 hooks, send hook and ingress hook. And then what I'm going to do is implement this module actually. So let's go here. Oops, sorry, it's already open. OK, so here I've already implemented like the bare bones hook here. All I need to do is like go to this packet and encrypt each byte. So what I'm going to do is for builder I equals 0, I is less than payload len I plus plus, and then I'm going to say payload of I equals, I'm going to do a very super secure road 32 implementation. So that gets plus 13 modulo 256, right? That's it. This is my implementation of the encryption module. And then for the decryption side, I'm going to take the same thing on the ingress side, put this here, and just this becomes 256 minus 13, right? This should decrypt it. Okay. Oops. And then finally, I'm just going to go to my implementation. It's a simple implementation. And then I'm going to insert my module. Let's insert it before checksumming. So checksumming is done with the encryption. So I can say encryption module instance dot init module. And this is a simple module, doesn't need any new fields or whatever, but they can also be added. OK, let's just compile this and look at how a stack looks like. Modified a header, so it's compiling everything, but it should not be too long. And then I'm just going to quickly compile a test case. It's generating a new protocol. So let's just look at the generated protocol. Let's look at the send function. And we can see towards the exit side, we have a crude loop that's iterating through each value and is doing our route 32 encryption. And on the ingress path, when it comes in, the packet comes in, it basically again iterates through those packets. Oops, sorry. Iterates through those packets and does the decryption, which is should be here. Yeah, there we go. It's doing some decryption here. Again, these things can be optimized further if we need to. So that's just the simple demonstration that extending NetBlocks is also as easy as just picking features and writing your new library implementations. Okay, but then let's get to the evaluation quickly. So we evaluated our performance of our stack on a real Nginx unmodified server. No lines of change to the Nginx server. I'm just going to zoom in onto this new protocols. The same result as before. You can see that as you pick and choose features, the performance gets a gradient, and you don't have to go all the way to TCP to get the full features. You can pay less features. We did a similar evaluation for throughput, where you can see that the throughput drops a lot when you have reliability enabled, so you don't have to pay that whole cost when going from UDP to something that's smaller. And finally, I just want to quickly talk about where BuildIt is going. So BuildIt is currently expanding in all directions. We are adding a lot more DSLs on top of it. Breeze is a regular expression DSL, Shim is a compression DSL, and obviously NetBlocks. It's also expanding downwards. We currently support generating code for CPUs and GPUs. We're adding support for FPGAs. And it's also expanding sidewards in that we're adding a lot of toolchain support to debug your code better or automatically migrate your existing code bases into BuildIt without any lines of code change. I like to call this the Quasar of BuildIt because of the way it's expanding. And finally, that's our website. If you have any contributions or if you have any questions, please reach out to us. Always welcome. Thank you.
We have time for one or two very quick questions.
Yeah, so this is an interesting talk because basically what you're doing, if I understand it, is you're taking ideas that were originally pioneered in the context of programming languages like AOP, stage compilation, even all of this stuff where we're doing data structure layout, and you're making it, in some sense, available at the source code level to anybody who doesn't have to get in the compiler to do it.
Yep.
I'm curious how much expertise you think it takes to use these things that way, and how much else is going to start migrating out of the PL.
Right, so the expertise-wise, I think the majority of the expertise that we need is a domain experts. The domain knowledge is all you need because if you can write a library for your domain, you can write a compiler for your domain. That's the sort of big agenda we are trying to push. And I mean, we have had my master students working with me who have implemented entire modules into this, like compression, encryption, and so on. And yeah, I mean, they picked up the system pretty quickly. If that answers your question, I don't know. Okay, we can talk later.
Really cool work. Your idea of sort of defining these views of the underlying packet data through this code that you then eliminate through staging makes one wonder, is there a reason to update the views? Do you ever have to modify the packet through these programs you're writing?
Yeah, so we have set integer and get integer kind of functions, so they can manipulate those data using those views. Are you asking about changing the views themselves?
We can talk offline. I was just curious if you thought about other abstractions for defining those sort of getters and setters that.
I would be interested in like talking about that. Yeah, cool. If you can extend it further. All right. Thank you so much.